Hello, good morning, good evening, good afternoon, everybody, wherever it might be. It is my great pleasure to welcome for the second time Paolo CARRILLO, and today he's going to tell us everything and more about deformation-groupoids and the Baum-Connes assembly map. Paolo, the floor is yours, the Zoom is yours, take it away.
Thank you very much, Peter. Thank you very much for the opportunity that I can speak here again, and we'll try to do better this time by explaining more things and going in some details. So please don't. You can stop me whenever you like. I will try to be. I mean, I hope I won't be very basic, but sorry for the experts. But I will tell you about my recent work with the Bailin Wang and Han Wang we give some formula for the pairing of the left-hand side of Baum-Connes map with the cyclic cohomology for discrete groups. And but before arriving there, I will try to motivate what is the main idea behind all these results. Is about the use of groupoids, even if we do it for discrete groups. So let me start with the motivation. Okay, so in the first point, I will tell you about the motivation of the work. Sorry, I will recall you or what is the Baum-Connes assembly map. Maybe Paul Baum is there, so I'm glad to talk about this.
He's coming. He's coming.
Ah, okay. So what is the Baum-Connes assembly map? Maybe most of you have heard about it, but if not, I will try to sketch the main ideas and mainly geometric ideas around this construction. So motivation, I will start with a discrete group. So let gamma be a discrete group for the talk. Discrete group. Okay. And in fact, under this condition, about Baum-Connes defined, I will recall all the ingredients, but define a map, a very famous map now in at least non-commutative geometry, but also is related to other things that I will mention. So define a map from I will do some left-hand side that I will recall what it is. So some group that is the left-hand side. It's called commonly the left-hand side of the Baum-Connes assembly map, and essentially it's in fact it's using their terminology, but I will recall the definition. In fact, is a K-theory of gamma. Well, it can be called like that. And so they define a map that is called the assembly map that depends on the group to some, well, the K-theory group of the C-star algebra. The C-star algebra, let me take for this talk, the reduced version. So there's a C-star algebra associated to any discrete group, which is a completion of, we call it, this is a completion of the group algebra, a particular completion, which is called the reduced C-star algebra. So this is the right-hand side of the Baum-Connes map. And okay, so in fact, sorry, we'll move a little bit the screen. So this is the K-theory again of K-theory of the C-star algebra of the C-star algebra of the group. And well, in the terminology that experts use, in fact, this already in Baum-Connes they call it like that. This is what the people call the topological side that I will also try to explain why this is the case. And here it's more the analytic side. How to call analytic side. And okay, so and this map is called the Baum-Connes assembly map. And the main motivation, before getting to the definitions, so the main motivation, at least for my talk, the main motivation is it comes from index theory. So from the classic Atiyah-Singer index theory, comes from index theory, as I will try to explain today, and try to get to the results, I hope. And I mean by this, well, the classic Atiyah-Singer index theorem, but also the family version that I will mention very briefly. This is just the first point of motivation, a family Atiyah-Singer version. And later on, it was motivated by some results on Connes and Scandalis, for example, or at least from my point of view, index theorem. And why, before, again, I'm just trying to motivate this first point if you just arrived, and I will explain the ingredients, of course, even I will do it in the second point for a point for gamma, that just a point, and try to motivate the ideas, the geometric ideas that are related mainly to deformation groupoids. But so before talking about the definitions, let me say that why this map is interesting. So why it's interesting to study this assembly map. Well, in fact, Baum-Connes conjecture this is an isomorphism to be an iso, and the conjecture is, as far as I know, maybe I missed something this month, but I didn't think so. Is still open, even if there's the conjecture is proof for a large class of groups, large families of groups, and sometimes the injectivity, the surjectivity. In fact, why it's interesting? Because well, this BC conjecture, so the BC conjecture, is implies, or it's related, implies, or at least related to conjectures, several conjectures in geometry, in geometry, topology, and analysis, and I will mention some of them. So, for example, the Novikov conjecture, which is a very famous one, which we still hear a lot of things related to it, which is related to the homotopy invariance of higher signatures. It also implies the famous Gromov-Lawson-Rosenberg conjecture on obstructions on the existence of a positive scalar curvature. In the analytic side, there's this Caddison, I forgot the name, maybe it's Caddison, right? Or Caddison-Kaplansky, maybe Caddison's conjectures, Caddison conjecture, and some others. In fact, there's some trace conjecture, which you can, there's a very nice paper on by Wolfgang Luke on this, maybe it's called the modified trace conjecture, but still it's very interesting for some group theoretic properties. So this you can look at some papers by Wolfgang Luke. Okay, so this is for motivating the why this can be interesting, and it's a main subject. It was for many years in non-commutative geometry, this link between topology and analysis. And I will now I'll give you the definitions. So how to define this morphism, at least from the modern point of view of deformation groupoids, and why it can be also interesting to do to take this approach. Okay, so let me see if I can change the page. Sorry, someone, how to change the page, in fact. Oops. Oh, sorry, I'm maybe here, right? Well, I don't know how to move the page. Sorry, I was thinking this was easy, but are you still there?
Yeah, we are, but this is your software. Yeah. I have. Oh,
okay.
Yeah, did you manage?
Yeah.
What did you click?
Yeah, it's in French. Put in a new page, so it's
inside une page. Okay.
Okay, so it was easy at the end. Yeah, as I was expecting. So the second point will be the definition using so definition of BC map using groupoids, using deformation groupoids. So I want to really stress the point that even if I'm going to define to tell you how to define the Baum-Connes assembly map for discrete groups, even there, it can be interesting to use groupoids, as I will try to convince you by giving you a explicit formula for the pairing of the left-hand side with cyclic cohomology. So So yeah, this it's not just about, it's not because just the group is a groupoid, which is obvious, but I will try to explain you how to use groupoids ideas to define the map, but also to compute the map. Some parts of the, well, some applications of index theoretical formulas. So okay, so the definition of BC, and I will start with a with a very simple example that will give the general idea, I hope. So in my first example, I will start just with a 1-point group. So as a motivation, and I think with the deformation approach, I think it will be enough to at least tell you how to pass to the general case. So in this case, well, the right-hand side is just so the K-theory of the C-star algebra of a point is well, it's just the integers if you're in even degree, and if 0 if not otherwise. Okay, and okay, this is I guess mainly known by people in the audience, but K-theory group of the complex numbers, because this algebra is just the complex numbers in this case, and this is just the integers. But what about the left-hand side? Well, in fact, up to now I have not really talked about this, but in fact, the approach that I will use is based on the original approach of Baum-Connes in the original papers. They were trying to, well, they sketch, in fact, they gave the fundamental ideas of how to define the left-hand side using index theory ideas. So assembling maps that I will try to do it today. And in fact, there was a definition in their original papers, and but what's afterwards called officially the Baum-Connes map, it was formalized using KK theory. So, but the original ideas of Baum-Connes, well, they stayed there. And in fact, it was for us, for Weiling Wang and Han Wang, and for me, very important to recover these ideas, because these ideas, together, of course, with the analytic version of the map, are essential. I mean, to put them together to compute at the end. So, what about the left-hand side for a point? So the left-hand side is the motivation is to assemble. So the motivation for the left-hand side is a Thiele-Singer index. So for this, I will. So I'm not defining yet the map. So I'm not defining yet the group. Sorry, I'm not neither the map. So take a M as spin C closed manifold. So in this situation, you have a map from the K theory of M, so the topological K theory, or the K theory of the C-star algebra of M, which is just the continuous, the algebra of continuous functions on M. So here you have a map that goes from a, well, because it's spin C, there is a Thom isomorphism in K theory, which goes to, for example, the cotangent bundle. And then, well, at Thiele-Singer, they defined a map, which is called the Thiele index morphism. So this is a Thiele-Singer index morphism that computes the Fredholm index of elliptic pseudo-differential operators. So in fact, they introduce all this machinery to codify the index of the elliptic operator. So why this is a motivation? Well, because the Thiele-Singer index formula, as you might know, or index term, is about a computation. So a computation that, in fact, computes this map, because this map I will call it here. This map is, in fact, I will call it the PM strict, where PM is just the projection to a point. So this is just the K theory of point, right? So a Thiele-Singer, in fact, Thiele-Singer theorem, and then formula, it's in fact about it's in fact about assembling. I will explain what I mean by this equality, but it's equal to assembling the different PM tricks. So what I mean by this, I mean by Atiyah-Singer term being equal to assembling. Well, I mean that here I took an M, a particular M spin C closed manifold, but if I change my M by so if I take a function from M to a different N as above, so a smooth map, and between manifolds as above, so closed spin C, then in fact Atiyah-Singer is a theorem. So the theorem for Atiyah-Singer, which is an equality of some topological index, some analytic index, is in fact equivalent to what is called now well, in fact, is equivalent to the functoriality of the following diagram. So to the commutativity of the following diagram, essentially. So for a smooth map, I will put good enough, because the maps for which one can define this kind of strict maps, which I will explain. In fact, this is again motivation, but I will explain using groupoids how to define these maps. But in fact, the Atiyah-Singer index term is about in fact, more generally, it's about the commutative, what I will call the wrong way functoriality, which is in fact the fact that one can associate these strict maps, which are family indices. In fact, this F strict is in fact what Atiyah-Singer called as just the family index, and the Atiyah-Singer theorem, and in fact the family version. This way of presenting things is motivated by essentially by Connes-Candalis, which was at the time already using groupoids, but in a different version for liations. So the functoriality means that this property, right? So well, this is for motivating the left-hand side, because assembling, what it means is assembling for, it will mean, well, put together these F stricts, these push forward maps that relate different indices. So in fact, what I mean by assembling is that then the wrong way functoriality, because so that means this property implies that I can define the following group. Remember, I'm dealing with the group with one element, but the idea will be very similar for in general. So I can assemble. So that means that, well, assemble for me is I will take a limit, a direct limit with respect to the topological K-theories of these M's, of these different family indices. And in fact, well, this is the group. This is the left-hand side. So this is in this 1 point case. And the assembly map in this case, which is, of course, an isomorphism, is very well known. So this is just for a point. So the assembly map is given by, so an element here is essentially the class is a direct limit of groups. So it's in fact a class of NEM and some K-theory element in some topological K-theory of M, spin C. So essentially, up to Thom isomorphism is the symbol of an elliptic pseudo differential operator, and in fact, the map is just the index. So this in this point 1 point case, this is just the integers. So this is the left-hand side, and so well, to get to the general case, I will tell you how to define these strict maps, because I just up to now I told you that if you have these strict maps that gives somehow the family indices of Atiyah-Singer, and if you show that they are functorial, then you get these groups that you can, well, these groups that they are assembled by the strict map. Of course, you need the functoriality to do this. It's essential to define the group and also to define the map, that the assembly map is well defined. So that's it for the point. So in fact, this is the case for a point. And I will tell you how to go further to the general case. But since I hope I'm not being very basic, but that is, I wanted really to insist in this talk more in the geometric ideas coming from deformation groupoids. So how to define the Schrick maps. So in the second point is I will so definition of F Schrick, which is called the Schrick maps. And the functoriality and the wrong way functoriality, which is at the basis of this approach. In fact, the idea of using deformation groupoids was initiated by Hilsum and Skandalis, but in fact by Connes, but officially in the first paper that at least I've known is a paper from '87 by Hilsum and Michel Hilsum and George Skandalis. And then in Connes' book, in the red book, he sketches how to use these ideas of wrong-way functoriality and deformation groupoids. So to tell you how to define F Schrick geometrically, and how I will put the first point, which I will explain you what a deformation is, and well, geometrically, but then you will see that there is a counterpart in the sister algebra that will give the indices and so on. So in the first point, I will talk about the deformation to the normal cone, which is now appearing in a lot of non-commutative businesses around the use of deformation groupoids. And so this is in fact a functor. So it's a deformation to normal cone, which I will assume by D and C functor. And the idea is it's very basic. So I will take a couple of manifolds. So manifold, it's a manifold M and a submanifold. So this is just a submanifold embedded in M. So what is the D and C construction? Well, in fact, is the fact that in fact the following set that I will define you has a infinity structure that I will give some details. So the set is the following. So you take the normal bundle of X in M. So X is embedded in M. So there's a normal bundle. So this is a normal bundle. And this joint union with M times R without 0. And so in fact, what is important is that it has a C-infinity structure with good properties. So in fact, essentially, I will mention two, so such that this part, it has with its product C-infinity structure is an open submanifold. It's an open dense submanifold. The part of the normal bundle is in fact of course closed because it's the complement, but it's a closed. But what I mean here is with its classic topology. So the normal bundle is a vector bundle over M. So it has a topology. So it has also a manifold structure. So what I'm saying is that seen as in this deformation to the normal cone, it's closed. So what is the main property of this construction, and why it's interesting in non-commutative geometry? Well, because the first property that one can show, essentially is really a differential geometry exercise, is that this construction, D and C, is natural in the following sense that I will explain. So meaning that, so I will explain what I mean by natural. So you have a map. If you have a map between couples of manifolds, meaning that you have a map essentially from M to M prime that sends X to X prime, but C infinity. If you have a C infinity map like this, then this induces a map that I can call DF. So it's with good functoriality properties. So it's also a C infinity map. which is explicitly given by F. In fact, it's just essentially in this deformation to the normal cones there are two kinds of points. Once for which epsilon is different from 0. So because I'm taking R star as a component. So here essentially the map is just F M epsilon. And the other part, so in the normal bundle, so there's a normal vector. Then here you have to take the derivative of F in the normal direction, evaluated at X. And this is well defined because F of X is included in X prime. So the differential between the tangent bundles, it passes to the quotient and gives a differential in the normal direction. So this is functorial. So it's meaning that well if you compute this for two maps, then you have a good composition properties. This can be shown more or less classically with just differential geometry purposes, but it has a very fundamental property for non-commutative geometry, because I will state two corollaries of this functoriality, which are essential to define Baum-Connes in these settings of using Deformation-Groupoids. So the first corollary 1, is that if I take an immersion of groupoids, which I will give a particular example of this, but so I won't come to what a groupoid is. Sorry, one has if someone has questions, then you can stop me. But if you have two Lie groupoids, in the sequel, I will use very elementary groupoids for defining in the case of discrete groups. But the property is more general. So you have an immersion of Lie groupoids. Then the deformation to the normal cone construction, since it's factorial, it gives you a way to apply it to the entire immersion. So that means that there is a Lie groupoid. So this is the entire word that is essential. So that means that I will define a new groupoid, which is called the normal groupoid. Maybe you have heard about the Connes tangent groupoid, which is a particular case of this. So this is as a set is in fact the normal bundle of G1 and G2, and so this is just the manifold, the deformation I was that can be applied to immersions. In fact, sorry, this is just R plus. There's a Lie groupoid structure over this. So this is in groupoid. This notation means the units of the groupoid. G2, 0. So the units of G2. And up to now, you can say, well, this is just a differential geometry result. But as I will tell you, the corollary 2, it will bring us already to non-commutative geometry, because this says that. So this is corollary 2, that in fact there will be indices, so maps between the K-theories of the C-star algebras. So the corollary 2 is about deformation index morphisms that we called those deformation index morphisms. So in the situation above, in fact, what one can consider, for example, the C-star algebra of a groupoid, of the groupoid phi, G phi. Maybe the best is restricted to not to the entire R, but just to the closed interval 0, 1. And then you can show that well, that there is a short exact sequence of star algebras. So, well, maybe in the groupoids I will take maximal or reduce it's not important, but in general one has to take some care about completions. In principle, these are maximal completions, but sorry, this is This is this normal bundle. And here you have the kernel, which is in fact geometrically computed by what it's in the other side. So this. So there exists this short exact sequence of C-star algebra, and in fact, since this algebra is contractible because of the presence of this open closed interval, in fact, when you apply K-theory to it, so the six-term short exact sequence of K-theory, in fact, this evaluation at zero becomes an isomorphism. So that gives so there is a short exact sequence of C-star algebras that gives a map from the K-theory of G1n to the K-theory of G2, which is essentially, so I will call this index phi, and in this talk I will define it as, so the evaluation at zero, well, the induced morphism in K-theory, which is invertible because I was saying this is contractible in K-theory. Sorry, it's contractible, so in K-theory is zero. So the K-theory of this, because the homotopy invariance of K-theory is zero, and then I can take a composition with evaluation at one. So this map, well, these maps are nowadays very useful in index theory and of several kinds, because they compute a lot of known indices in the literature. So in fact, this gives this kind of maps, which are then defined geometrically by some groupoids, in particular by this deformation-Groupoid that I will circle here. So if you know this groupoid, and its C-star algebra is essentially just a continuous family of C-star algebras, and then you have these indices. Now, if you have the good properties under good conditions, that will be satisfied the latest in the sequel. So, for example, amenability in some cases and some spin C conditions, then you can in fact go from G1 to Gn to G1n by some Thom isomorphism. You need good conditions, so meaning that some spin C conditions and something good. So these maps, in fact, well, now I will tell you now what this is, how use these maps to define the Schrick maps. So,
before you flip the page, I have a very silly question.
No, go ahead.
So here I have this C-star of Gn1, and I understand that this is the normal bundle of 2G1 in G2. So yeah. How do I assign convolution C-star algebra to a normal bundle? Is it obvious?
No, in fact, this is a good question. Because of the groupoid structure, in fact, this normal bundle is a groupoid over the normal bundle of the units.
Okay.
Because the immersion, in fact, the units embeds into the units. It's not obvious, but it can be proven by hand. So in fact, the structure of the groupoid is not just as a vector bundle. In fact, it's a vector bundle over another vector bundle.
Yep.
And in fact, the source and target maps are given by the differentials of the source and targets, but in the normal directions. So in fact, it's also a convolution groupoid.
Okay, great. Thank you so much.
No, thank you for the question. In fact, this is also in the literature called VB groupoids. It's a particular case of this kind of objects, which are vector bundles. Of course, a vector bundle is also a Lie groupoid, but here is in fact
a different structure, right?
Yeah. In fact, this is a vector bundle over a vector bundle. So this is exactly is important. Yeah. Okay, so this is a particular, well, this is a general case, but I will apply it to to a particular case that will give us the Schrick maps, and then the Baum-Connes. Well, now I'm not putting groups yet, so just to explain how to define Schrick morphisms for functions. So in fact, this is my point B. So I will explain you how to define the Schrick maps and some very brief comment about why is functorial. So given F a smooth map, infinity smooth map, well, one would like to define the Schrick map. Of course, if I don't put groups or whatever, I can do this as was done by T.S. Singer at the time. That means to enlarge, take some more space and take some normal bundles and so on. But here I will use these deformation ideas to go further, because the construction of a T.S. Singer cannot be applied in the equivariant case so easily, and even less in some other cases, as I will say, I will mention later. So this is again the idea of Connes that he sketches in his book. So given this, consider the following diagram. So in fact, I want to associate the F Schrick map. I tell you how to define it as a particular case of what I said before, an immersion of groupoids. And this is again, from my point of view, where it's essential to pass to non-commutative geometry, even in this case, because the function f is not necessarily neither injective, sorry, it's not an immersion or neither a submersion. Because if it was a submersion, usually Schrick maps, for example, are are the counterparts of integration along the fibers. But since we are assuming anything, I need to do something else. So in fact, the idea is to replace this f by a non-commutative version of f, which is in fact just very easy. You will see. I will just define this map. So f times diagonal. This is a very easy map to define, but in fact the point is that from this m times m here is not the product manifold m times m. In fact, it's the per groupoid m times m. So this is very important, because at the level of algebras, this will be like tensor with the compact operators. So it's not here. I'm passing already to the non-commutative world, because of course the map f factors to this. Here you have a projection to a point, but in fact, this projection to a point is in fact is a Morita equivalence of groupoids. That also this is reflected, of course, in the algebras. So the K theory, the compact operators, the algebra of compact operators is Morita equivalence in a good sense to the complex numbers. But here I'm just talking about geometry. So what I'm saying is I replace this f by some map, which is in fact the same in the differentiable stack world. So in the groupoid sense, they are essentially the same. So in fact, formally the same in some category. So because these Morita equivalences are the isomorphisms in some nice category. So in fact, these f are the same. And I will use this new one, because this new one is in fact an immersion of groupoids. So f was not an immersion, but now I'm transforming it, just taking more space, and this is an immersion. So I can get I can apply the construction I mentioned in the previous page, and I will tell you in this case how it looks. So remember, I was taking the normal bundles and so on. So for example, here the normal bundle can be identified to, oh, sorry.
You mapped your screen to a point.
So I think my screening, what happened with my screening? I think
you have to share again.
Yeah, sorry.
You unshared your screen.
Sorry for that. Whoa, I will. Okay. Let me see. Okay, I have it. Can you see it?
Not yet.
Okay. Right there. At least I recovered, so it should be now there. Yeah.
Yes, we've got it.
Ooh, perfect. Thank you. So I guess. Okay. It was not erased. So that's great. Okay, so
Paulo, before you continue, so your M and N are compact, right?
well,
If not, your F has to be proper, right?
yes. In fact, for the moment they are not, but for index theories purposes, later on they will be, or in the when the group will act.
No, when you want to define the F lower shriek, F has to be proper, right?
No.
Yes, it does.
As I define it using this morphism is not.
Well, no, there is no F low. F has to be K oriented, right? In some way.
Oh yeah, sure. Yeah.
For that, it has to be proper.
Yeah. But I'm not yet defining the Schrick map, just the groupoid.
Yeah, okay. Groupoid can define. Okay. Yeah.
The groupoid is sorry. So yeah, you have the normal bundle in this case identifies with this. So then of course we will see how to pass from M to this bundle. Exactly, you need some condition, of course. So here you have a well, I'm just applying the construction I gave before, right? And this gives, so this is it's a deformation groupoid that gives the following map using under some conditions. So under K-orientation condition, meaning that essentially I need to pass, I want to pass from Km to the K theory of this bundle somehow. And then I need some condition. So I need some conditional, being this spin C or something. Yeah, that's where the condition enters. And then I apply my deformation property that I define it later. So it's just in this case is the deformation of F. And I get to the K theory of the C-star algebra of this groupoid, which is essentially up to Morita. So in principle, this is a non-commutative object because there's this pair groupoid. But in this very easy case, this will give a copy of the compact operators. So up to Morita, which is in this direction very easy, up to Morita is the K theory, the topological K theory of N. So this is what is called the Schrick map. So up to here is F Schrick. So of course one can show using well now we understand it better. At the time of Connes was just sketchy, but this is of course the Atiyah index, the Atiyah family index in this case, if the M and N are compacted. Okay, so and of course, well, I'm not yet to the group case, sorry, but of course, you don't need this technology to define the subjects again, if you're not dealing with groups or so other objects. But what you can prove that, in fact, Atiyah Singer essentially proved this in the family case, that this is functorial. So it's functorial. So again, this is a Atiyah Singer family index theorem. And okay, so that means again, but the idea of using groupoids and this deformation business is that the idea of the proof is because the indices are just given by some natural maps. So I want to come back. It's just evaluation maps with respect to some appropriate deformation groupoids. So in fact, the proof of this functoriality is based. So this is just based on properties. Sorry, let me see my notes. Based on the well, on groupoids, on the groupoids we had, but essentially on basic cohomological properties. Sorry, I'm missing the name. Cohomology, well, properties, sorry. Which properties? Well, essentially, well, the existence of Thom isomorphism in K theory, homotopy invariance, escission, maybe escission is even, well, Morita invariance, essentially. So that the fact that two groupoids, well, two algebras which are Morita equivalent have the same K theory, that's the basic properties, and well, this the existence of the six-term short exact sequence. So this suggests, in fact, that well, that this if we manage to define these Schritt maps using almost the same ideas, then the proof is the same. In fact, in other contexts, this is what that we do. We did with the bilingual first. So this is what I want to go now. I will just checking my time. So this is just for a point. Well, sorry, it was just for families, but now I want to tell you how to pass to the general case, at least the ideas. You will tell me if it's very basic, but I hope that if there are some students there, it's good to have this, at least some details. So what happens for gamma discrete? So now, if I will take again these groups, and what I want to consider now is F maps, appropriate maps again, which are gamma equivariant and between nice manifolds or with good K orientation properties. In this case, I want between gamma proper spin C compact manifolds, so on, to have a nice properties. Well, the point is that again, what is key in this approach is that the deformation to the normal cone construction is functorial. So the functoriality of the deformation to the normal cone construction, functoriality, implies that there is an action, there is a semi-direct product groupoid. So in fact, there is an action of gamma on the entire gamma of the entire deformation groupoid that I defined before. So this is it's an easy observation, but it has deep consequences because, well, you have essentially here is a semi-direct product. So it's not an action groupoid. So this is just a zero. But it's based on the action of gamma on the groupoids, not only on the manifolds. So it's, because in the previous case, in fact, I use groupoids everywhere. Even, okay, the manifolds are also groupoids, but what I mean by the gamma acting on G, on this deformation groupoid, is that it really acts on the groupoid, not only on the manifold associated to the groupoid. So with this observation, in fact, one can show that, well, essentially, this is what I did with a bilingual some years ago. So I will try to. This gives a Schritt map between, at least as I put it, in between the C-star algebra of M cross product with gamma. Remember, these M's are proper manifolds for the moment, and here I will put N. This gives this, and the theorem that I proved with bilingual, so some years ago, bilingual, perhaps 2012, so already 10 years ago, is that well, fx is functorial, and even for more general groupoids, even twisted groupoids. But I'm not yet to the, in fact, what I want to talk today, in fact, was more about the recent works with Bailing and Han Wang, which is a preprint in the archive. But the point is that, well, this functoriality, this wrong-way functoriality allows to do a lot of things because, well, first, it implies that the left-hand side of Baum-Connes can be defined. So it means that, well, as using the Schrick maps. Of course, you can ask if this coincides with the other models of left-hand sides, and it does. I would say some words on it. But so you take this M as above, so gamma, proper, spin C, co-compact, and you assemble these things. So you have two consequences of the functoriality. The second is that the assembly map is well defined. So the assembly map here will go to the sister algebra of gamma, and essentially it will be the same definition, but the index is a gamma family index. In fact, this is already called like this in the original papers of Baum and Connes. They gave the fundamental idea of defining this exactly as a gamma equivalent indices. So this is the assembly map. So as a corollary of the functoriality, one gets this, that you can assemble the groups and you can define the assembly map. So these two are corollaries essentially of the functoriality. But what consequences of this? So, well, this is what I want to pass to my point 3. So applications of this approach. So this is just the definition of the assembly map. And I will tell you some things that then we can also do, because otherwise it's just another definition of Baum-Connes. So applications of the deformation approach, of the Deformation-Groupoid approach. So remember that in fact here gamma is just a discrete group. So the groupoids are beneath the definition. So the first application I want to mention is in fact my, well, I will resume it. It's my work with Bailing Wang and Han Wang, which is I guess in 2021, but it's still on the archive. Okay, so well, the first thing is that since we are dealing with groupoids, one can well expect to use these techniques for different functors other than the K theory of the C-star algebra. In particular, for example, for cyclic periodic cohomology, if you have appropriate algebras. So the point is that with appropriate algebras, let me see just my time. Yeah. Well, appropriate smooth algebras.
Sorry,
Yes.
Paul, can I ask something? Your
Yes,
point number 1, right? You're just slightly high up, one line up on your slide.
Sorry.
Just go one line up. Yeah, this one. This looks very much like the theorem of Esterhoff, Schaber and Esterhoff.
Which theorem?
The number 1. That the Polska K homology is the direct limit of K theorem of cross products where M is proper, where gamma is properly on M.
Certainly it is, because in fact they coincide. But here,
so it is the same theorem, right?
It's the same theorem with a different construction of F Schrick. But so it's a different.
I thought of okay, somehow.
Yeah. So in fact, I mean, to try to answer.
But wait, by the way, so F Schrick is actually, now if you talk about history, it's really due to Grothendieck, 60s.
Perhaps, yes. In fact, it
okay,
comes
so
from
and it's the same construct. It's basically the same construction.
It's basically
so maybe,
the same. Yeah. In fact,
precisely.
In fact, Connes he gave a sketch in his book, and also by Baum-Connes using index terms ideas. But yeah, I guess it comes from even before. using
Yeah, but basically, actually, they really refer to Grothendieck, and Paul tends to, when he used to give lectures where he said that this is something which Grothendieck constructed, and Grothendieck got it right for the first time.
Okay.
Right. So yeah, but okay. So this is the same result. Yeah. Okay. Fine.
Yeah. In fact, of course,
Yeah.
with a different formalism of these deformation-Groupoids, perhaps the expression of the group might be different, but in fact, at the end is the same. In fact, in my point one, if you want, for me, it's a definition using deformation-Groupoids, but one can prove that in fact this, of course, coincides with the other model.
Yeah, I know, right? Yeah. So yeah.
So this is but it's an important question and remark because.
And we actually could do it with coefficients, right?
Sorry.
So you can do it with coefficients. So take any separable gamma algebra.
Yeah, I guess. Yeah.
And you can do the same thing with coefficients. The same.
Yes.
The result is the same.
The result is the same. Yes. Now, what I'm yes, it's the same.
Okay, guys, since we are at it, Paolo, could you please explain a little bit more how you get this limit? So what is your variable, you understand, is your m, and you have an action of gamma on m, and f goes from where to where? I'm a bit confused about this. The very construction of a limit. The
limit is, in fact, you can think of the as the free group, the abelian group generated by the following relation. So you take a couple of a cycle here is in fact manifold M with these properties, and X is in fact in the K theory of this group, right? And I will relate it. So I will take the equivalence relation generated by the Schrick maps. So if F is M, it goes from M to M prime. Then I will say that X and F Schrick, which are two different K theory elements, are related. Okay, so in fact, you can think of this as these are the cycles under this equivalence relation. So two cycles are equivalent. At the end, this is generated by. So that means that two cycles are equivalent. So you have two different cycles here. Sorry, X is not in M. X is in the K theory of an X prime. Then they are related if you can find an M double prime.
Can I make a comment?
Sure. It's
what? Is it possible to make a comment?
Yes, of course. Go ahead.
Sure, Paul. Go ahead, please.
Well, first of all, as Richard said, this whole F lower Schrick thing, this was done by Grothendieck. But I don't know if I'm getting through here. Are you hearing me?
Yes, you are getting through, yes.
We concur with you.
Yeah, as Richard said, this was all done by Grothendieck. So this approach in this very interesting talk that we are listening to, this is in fact very closely related to what Grothendieck did. However, there is one new element here, which is the deformation that Grothendieck did not have, which is the deformation to the normal bundle. And that new element is very extremely useful and very enlightening. Grothendieck did not have that. But in papers by Fulton and McPherson and me, we did introduce that within the context of algebraic geometry. And this allowed us to extend the Grothendieck-Riemann-Roch theorem to algebraic varieties, projective algebraic varieties, which are allowed to have singularities. So there is a new element here. There is something new here which Grothendieck did not have, which is the deformation to the normal bundle. But the whole F lower Schrick and all that, as Richard said, that's Grothendieck. That's all Grothendieck. In his classical paper, which was written by Borel and Serre, about Riemann-Roch.
Okay.
Okay.
All right. So all right. Okay.
Yeah,
No,
thank you
but I
very
want to
much.
have a comment about this.
Thank you very much.
I
For
mean, in what you are saying here with the F lower shriek and all that, there is another approach which gets rid of this F lower shriek and all of this thing, which this involves giving a direct construction without taking direct limit and so on of the left-hand side. That is, you take pairs M comma E, where M is a spin C gamma manifold, E is a gamma equivariant vector bundle on M, and then you organize that into a group, and you put on the equivalence relation generated by Bordism, direct sum disjoint union, and vector bundle modification. I mean, this is a much more direct approach, which allows you to bypass all this formalism of the F lower shriek. It also allows you to bypass the deformation to the normal bundle. But I would strongly recommend, if I might, that this is a much simpler and much more direct approach. You take pairs M comma E, where M is a spin C gamma manifold, which is gamma compact, proper, and gamma compact, the quotient. And then E is a gamma equivariant complex vector bundle on M. You organize these into an abelian group using the equivalence relation for K homology. That is, there are 3 steps: Bordism, direct sum disjoint union, and vector bundle modification. And this, I think, gives a much more direct approach. You bypass all this formalism of the F lower shriek and the, I mean, it's in there implicitly. Implicitly, all of that is in there. But I think that is a much more direct approach, in my opinion. And then the assembly map is taking the index, of Dirac tensored with E. So anyway, I'm just trying to say that Richard has been a very, as usual, has been an excellent historian.
Thank you, Paul. That history comes from you. I learned it from you. And I think we lost the speaker, right?
Oops, wait a second.
Where's the speaker? Wait, where's the speaker?
Where's the speaker?
Well, he vanished. So,
He vanished.
Sorry, Paul, you have to continue the talk.
Well, we also have Jonathan. Yeah. No, let's get back to our speaker.
Well, I don't have any special, I don't have his phone number or something. Let me pause recording at least.
Say this in there. A TN singer took some, some beautiful and wonderful ideas of Grothendieck and moved it over into topology and index theory and so on. I mean, Grothendieck's ideas, of course, were within the framework of algebraic geometry, but that was a wonderful thing that a TN singer did to move it into the geometry and topology of manifolds and index theory.
So, Jonathan, you said that this shriek is still hidden there, right? It's not gone away.
Right. It's sort of hidden in the definition of the. It's hidden in the definition of the map from the left-hand side to the right-hand side.
Mm-hmm.
Well, I'm not so sure about that. I mean, the definition from this point of view, if you take these pairs M comma E, you organize them into a group using the equivalence relation for K homology.
Right, but you have to show that the index is functorial, which basically comes down to pretty much the same thing. In other words, that you have to show that if you have 2 things on the left-hand side, two things that represent the same class, then they go to the same thing on the right.
Yes, this is you are absolutely right about that. That has to be done, and
So that's very
Yes,
much like showing the functoriality
Yes.
of the Schrieg map.
Yeah, yes, you are making a very good point. Yes.
Okay, he's back.
Ah, great. Our speaker is back. Eh,
And you have to unmute yourself.
Please.
You have to unmute yourself. Paolo, unmute yourself. Yes, good.
Yeah. Really
Good.
sorry. Yeah,
okay.
my son turned off the internet and it took a long time.
Okay, happens.
Yeah. Well, it was a break anyway, so, and it takes time, so.
But we didn't waste any time. We discussed the Schrieg map. So
Okay, that's perfect. No, in fact, thank you very much for the intervention, the question and the remarks, Paul. It's
Mhm.
extremely interesting to hear all this. So the screen is over there. Can you
yes,
see it?
yes, we can see
Okay.
the screen. Yes. Mhm.
Yeah. I mean, yeah, I think what is also very interesting of this approach is that, of course, it has a long history, but and I want to tell you very briefly because I don't have too much time, but my point is that once you have these groupoids, the good algebras, you might expect to apply these constructions in for other functors. Other functors. In particular, I want to tell you my recent work with the ones that in fact will allow to. Well, maybe I can tell you what my goal is in some minutes at least to tell you how to define several things. The first is that I will tell you how to it's not the only way to do it, of course, but I will at least as far as I know is the formula we got is somehow new, but the formula is what about. So I will tell you how to define a Chern character with some kind of assembled group, which also I think it was somehow some survey by Baum-Connes, I guess. At least they mentioned the name of like the RAM cohomology for the discrete group. So I will tell you what it is, again, by assembling something. And then I will tell you how to define an assembly, a cohomological assembly for the group at the level of periodic cyclic cohomology. And this for every group. So of course, maybe you are tempted to fill the diagram, but this is of course very hard. But at least I will tell you how to define the map here that we call the Chern Baum-Connes assembly map, because as I will try to say very, very quickly, it's obtained by assembling Chern characters. So it's behind this idea, there's also a Riemann-Roch theorem, of course. But how to do it? Well, so again, with appropriate algebras, I mean that you need the smooth right algebras, and the right algebras to consider when you take this kind of groupoids I mentioned to define the Schrieg maps are, well, algebras which are somehow Schwartz in some directions. So, but this is again, you can see. In fact, I talk about this in a global non-commutative geometry seminar. So I think I gave some more details on over there on the algebras. So essentially, what we want is to define a Schrieg. One can, well, with appropriate algebras, what I mean is that the cyclic cohomology, the periodic cyclic cohomology has essentially the same properties as the K theory, if you have the right algebras. So you have the properties of homotop invariance, of Thom isomorphism in this case, and you have also well, this 6-term exact sequence.
Aren't you thinking about coefficients?
Yeah.
You want things with you want things with coefficients, not just for a group.
No.
Just looking at the group ring is so wrong, right? You're really thinking the coefficients, right? A cross gamma or something.
Well, yeah, this is M cross gamma. Yes. Yeah, okay. This is with coefficients. Yeah, in that sense, yes. This is the for me. This notation is the convolution algebra of this Lie groupoid, which is in this case is a transformation groupoid. But yeah, so the
yeah, but you think about the properties with respect to coefficients, right? It does not have to be commutative algebra actually.
Ah, no. not at all, in fact. Yeah. So the point is how to define these trig maps. And in fact, they are defined using this deformation to the normal cone groupoids, again, in the same way. So because it is essentially the same properties. So Thom isomorphism with some good Carry-oriented condition. And then the deformation.
All right, yes.
Yeah, sorry.
Just go on.
So in fact, in this case of discrete groups acting properly on manifolds and this crossed product algebra groupoids, there are computations which are known. This can be done in just in cyclic periodic cohomology with appropriate algebras, using the same kind of ideas, and then you can prove also the one-way functoriality, right? But in these cases, some things are known. In fact, there is in this case some kind of Hochschild-Kosten-Rosenberg theorem computations by several people. The one we took is in fact based by Tu and Shu, but that computes this as some it's called some delocalized K-theory, cohomology of the manifold. I won't have time to explain what it is, but essentially it decomposes as so the idea is to this is also comes from a lot of people. I cannot mention everyone, but this also appears most of these ideas already appear also in the paper by Baum-Connes, which is in the Fet of topology, which decompose essentially this as a well, you take the centralizers of elements and here you have to sum over some degrees and elements of finite order and classes of conjugation. Sorry. Well, this is more or less classic. I'm just putting here because I'm not giving the details, but this is quite a standard, I guess, in this business of cohomology. The point is that so if you take this model, well, in the other side, you also have this thing, the same thing. And so you have also a computation, a geometric computation. This is for discrete groups. In other cases, not all these computations are done, of course, but in this case, this is known. And in fact, well, again, by wrong-way functoriality, but again, based on the use of periodic cyclic cohomology. So there is where you do really need this ingredient to define the Schritt map and to show the functoriality. So this gives the wrong-way functoriality of the Schritt maps in HP, and in the delocalized version gives the possibility first of defining an assembled group by essentially the same ideas. So you take a limit, a direct limit, or by cycles of groups like this. So this gives this, and this also gives. This is something we defined again in this paper with Wang and with Bailing Wang and Han Wang. We can define an assembly map, which is essentially in the elliptic part of the cyclic periodic cohomology, which is in fact the cohomology of the group, but the delocalized version. So this is let me see my computation somewhere. Essentially, these are groups. These are group homologies of the gamma G's. Gamma G's is in this thing is just the fixed point group. So this is the H decentralizer, and you divide by divided by the group generated by G in there. So here I'm taking just the elliptic components. So that means that you choose for every conjugation class of some finite order element, you choose one of this. And in fact, this can be done in our case because we knew by Bourgaléa's computation that in fact this is a direct factor of the cyclic periodic cohomology of C gamma. This is a computation which in this case is known. Again, this is done by Bourgalea, but at least the first I know. But some other people did it also afterwards in more general cases, and taking again this ideas of Bourgalea, and there's also Karoubi that made a good contribution to it. And so essentially what you have is this, a map that goes from here. And if you well, together with a Riemann-Roch theorem, that is essentially the fact that up to some Todd classes, some delocalized Tom classes, the Schrick maps commute with some. So remember here I'm taking proper manifolds. So here I can the smooth convolution algebras are in fact stable under holomorphic calculus. So I'm taking proper manifolds. So one can prove, this is what is part of the paper, that in fact if you take here the Chern character that goes up to the localized cohomology of gamma of M, sorry. Well, this with some twistings, of course, of Todd classes. So here you have to put some Todd business class. So that depends on gamma. So in fact, in every G is easy to compute in every component. So I don't remember how we call it. I lost here my paper with all this internet business. I had my notes and well, there are some Todd classes here. I will just put it like that. And gamma. Again, this kind of proofs, in fact, if you are curious to see our paper, since the definition is given in terms of deformation to the normal cone constructions, the proof of this is in fact is conceptually simple, because in fact it's just it's naturality of the evaluations, because the Schrick maps are given using these deformation-Groupoids. So essentially it's just a naturality of the Chern character, essentially of the Chern cone character, and all where the Todd appears is just with the comparison with the Tom isomorphism as classically. But resuming all this, so if you resume all this Schrick business also in cohomology, so resuming, so what you get is a map. It's a map from to here to the elliptic component of the periodic cyclic cohomology. So let me just see abusive notation and take this as a factor of cyclic periodic cohomology. And it implies then that, well, you can define a pairing. So here is without any assumptions on the group gamma. It's just well, maybe countable, but yeah, countable, I guess. Well, you can give a form, you can give a pairing for any group. And
sorry, Paulo, but I'm lost a bit in your notation. So yeah, when I hear you have this Chern VC map, it goes into where? If this is some kind of homology of gamma with coefficients in where? What is it?
In fact, it's a notation. It's in the finite module components. But if you want, for our definition, could be this definition. It's in fact the sum of homology groups of gamma G's with a fixed G of finite order in a given conjugacy class.
I'm perfectly happy with the right-hand side. Yes, thank you.
And this, again, as I was saying, this is one factor of the cyclic periodic cohomology. The other factor is, in fact, depends on the infinite order elements, and it doesn't appear here in the pairing. It's here. And okay, so in fact, again, this approach allows to do this, and it's not easy. Of course, you need the appropriate algebras, but once you need you have the appropriate algebras, the exact same groupoids and the same kind of proof works. Using this for me fundamental idea of Connes that essentially the cyclic periodic cohomology is essentially K-theory.
Sorry, but once again, so I'm slightly confused with your last line. So, well, it's not true for overclasses in HP star, right? You can kind of you quotient out by something. You throw out some classes.
In this well,
in this formula, it's just well, it's not true that there's pairing of algebraic cyclic homology of a group ring with topological K-theory. It does not pair, right?
Well, this is not. This is just the pairing is defined. I will say it how it is, only with the respect to the finite order elements. The finite order.
So you only look at the elliptic classes in HP star. Okay.
Yes. Yeah.
Okay.
The other ones.
You don't look at the others. Okay.
The others no. In fact.
Okay.
Well, I can define it as 0. This pairing, but.
Yeah, but no, but that's just to make sure that's what you do, right?
Yeah, exactly.
Yeah. Okay.
So in fact, the point is that all these things allows to give the pairing. Of course, yeah, define it as for well as 0 if the element comes from the infinite order part. But what I want just to end this talk with is to give you the formula. But that again, this is something I talked about in the non-commutative global seminar. Maybe some of you were there, but I will at least give you the formula and say this is and say another further directions, another future directions that can be done. And but the formula of the pairing. So this is the main result of the paper. Formula for the pairing for finite order elements is the following. So let me just take my notes here. So essentially, it's a geometric thing. It's again, in fact, it was for us, even if it's not stated like that, is based in the Connes-Moscovici approach to this kind of problems. Because even if they don't talk about groupoids, for me at least, there are groupoids everywhere in their computations. But well, now we managed to assemble all this in using algebraic topology tools, because here in principle, as you could see, the analysis is hidden, because I will give the formula without making appealing of the analysis, but making use of the functoriality of the Schrick maps. So essentially, this is the Atiyah-Singer approach, the classic Atiyah-Singer approach. So the formula for the pairing is the following: for a gamma G, which comes from well, one of these cohomologies, gamma G. So by Bourgalea's computation, this is enough for G of finite order, right? The other ones are 0.
Yes.
But perhaps they are interesting, and in fact, I don't know, because
well, they are non-trivial in general.
Yeah,
actually,
it seems so.
right? But
so, yeah, right. In fact, yeah, for many groups they are not, but in fact, there are known examples indeed where these other components appear. But well, at least for the finite order components, the formula using what we did, at the end what we get is a Schoen-Carrington of M, but the component localized at G with the Todd isomorphism localized at G, because the cohomology delocalized with respect to these classes. And then here I have also pullback, where I will tell you what it is. Pi of G is in fact a projection. I will state it in terms of groupoids, but a projection. So the centralizer acts in the fixed point manifold, MG. MG is the points that are fixed by G. And in fact, there is, again, the groupoid language becomes very useful, because there's a canonical projection from this groupoid to this group, which is just the projection, but it's a groupoid projection. So in fact, in groupoid cohomology, there's a pullback, which translates in terms of just of invariant forms. But so this pullback is what I mean here. So this is a group. This is the tau G lives in the group cohomology of gamma G, and then you pull it back to the groupoid cohomology of mg gamma G, which turns out to be the invariant gamma G invariant forms, because here we are taking proper actions. So these are known results. And well, this is the formula. So for every class. So this is what I wanted to tell you mainly. But just to finish this talk, so we can discuss of this. And to finish the talk, I want to tell you about the work that came after this. So essentially, the use of groupoids suggests that you can do more things. In fact, the Schrick maps, as I explained today, I did it for discrete groups, but in my paper with Bailing Wang, so 10 years ago, we did it for groupoids, for general groupoids. So further directions, just to end the talk. And some of them are work in progress, and some other are already almost preprint, I hope. But well, first, well, for general groupoids, in particular, it's not that we want to generalize like that, but there are very interesting cases. In fact, for general Lie groupoids, in particular, already groups are interesting. Of course, Lie groups. It's interesting to understand these things in this setting of deformation groupoids. Well, for general Lie groupoids, we already had this. So if you have a groupoid G, this can be done in the same way. Now the other part, the cohomological part, I don't know, because well, I know in some cases. In fact, one can Schrick maps. One can define this, and there is also a Schrick map, but under some condition, and I will tell. Okay, here is the convolution algebra of the groupoid. This I can do, for example, under some hypothesis, under some Thom hypothesis, I will say. In fact, as far as I know, because in cyclic periodic cohomology, there is a nice understanding of the Thom isomorphism. In fact, Richard Nest has a paper on that, and Nest Elliott, I think, someone else, maybe Nensuna, if I'm not wrong. And some other people afterwards explored this question on the Thom isomorphism in cyclic periodic cohomology. But as far as I know, there is no, in principle, should be, of course, related to Thom. But if you have a Thom isomorphism, as you have, for example, in K-theory, or even in KK theory, as was explained by, for example, Legal using groupoids, then I can do this. So essentially, I believe that for all groupoids, you can do it. But I don't know if in the literature, the Thom isomorphism for G proper vector bundles has been properly defined. But if it does, then you can assemble the Chern-Kohn characters and define the Chern-Baum-Kohn isomorphism. Of course, to get a formula as the above for discrete groups is not so easy, because you need geometric expressions for the cyclic periodic groups, cohomology groups or homology groups, which is in fact done in the case of discrete groups by Burgalea and all these people that have worked for years, the HKR isomorphisms. There are a lot of things known in discrete case. In more general cases, well, I don't know too much. Maybe, of course, there are cases known, but in general, there is no. So this is one direction. This is in fact done. This is some survey I already wrote, and I hope to put some very soon in the archive. And the other thing is that instead of just I want to finish with this, is that there's another direction which I want to explore in the future related to index theory of more singular objects, is that instead of geometric cycles which use just manifolds, one can use orbifolds very easily. So this is a gamma orbifold. In fact, the construction adapts exactly the same, because orbifolds are, if you take a, because if the orbifold is represented by some étale groupoid, by G étale groupoid, étale proper étale, so with units M. So for orbifolds, you can consider the map. If you have a map between orbifolds, you still can factor by this diagonal. So it's not anymore a diagonal. In fact, this is not injective anymore, but in fact, it's an immersion, and you can apply the same construction. This essentially also was somehow, sorry, this is in the other direction, done by Hilson Scandalis in a paper on ground wave functoriality, but not to define exactly what I'm going to say, that you can assemble cycles using orbifolds. So you can consider a group as I defined, but using cycles which are orbifolds, and the assembly map is exactly the same. Of course, yeah, the functoriality works the same. And here you have, of course, a map which goes from the group I define it, because a manifold, a smooth manifold, is an orbifold. And okay, so it's interesting from the point of view of index theory, eventually, I guess, from Baum-Connes. But at least from index theory, yes, because one can expect to have the formula as I put it before for manifolds for the left-hand side, but using a left-hand side which is more refined, using cycles which are orbifolds. I guess this is not the first time, of course, in the literature that people consider morphisms like that, because in index theory for singular manifolds, there have been a lot of efforts to define indices in this same K-theory group. So at the end, higher indices here for singular objects. In fact, there's many works in which people have managed to define the indices. Now, to assemble those indices is exactly, it's more refined. So this is what we can do, for example, with this exactly approach for orbifolds. And well, I think that is what I wanted to tell you. Well, I have a lot of things to say, but I guess I didn't know any more my time. You know, I lost my head with this internet thing.
Well,
so.
you are basically right now exactly on time.
Okay, so thank you very much to all of you, and to be there somewhere.
Thank you so much for a great talk. Thank you. And now we can begin our questions. Tomek, go ahead.
My question is this: I know some version, very similar theory to your approach, which is about homotopy theory of groupoids and Mackey functors.
Okay.
Satisfying pull, push, or how is it called? Back-Chevalier condition.
Projection formula.
Or projection formula if you have products, but I don't know. Yeah.
Okay.
Could we say that what you are doing here partially is generalizing this Mackey functors formalism to non-commutative geometry? Because in the classical theory, there are no convolution algebras. So people are not speaking about the right-hand side of assembly map, but all this Schrick story is present in this theory.
But this theory is about groupoids, or, for example, Lie groups, because
groupoids. I know a paper about at least finite groupoids, but I think that the story is more general.
Well, in fact, I don't know the answer. It would be very interesting to see that. But you know, as I was mentioning, this Schrick maps for general groupoids. Okay, it works for general groupoids under this Thom hypothesis, but it's already very interesting for I don't know, so some Lie groups, maybe semi-simple connected Lie groups. In that case, the assembly map is known to be an isomorphism, but one would like to have a more geometric description. I know people are working on that, and of course, there have been a lot of papers in this direction. It's called the Kohn-Kasparov conjecture, and I think it's related to this Mackey business because the left-hand side is essentially given by the maximal compact Lie subgroup, and because it's but I would be very interested to see how it relates to this Mackey business, but I don't know too much on that. But I know these people that works on the Kohn-Kasparov things.
May I?
Yeah.
Okay, there is no Kohn-Kasparov conjecture. There is Kohn-Kasparov theorem.
Yeah. Okay.
Okay.
The people.
It is it is isomorph the case of Lie groups.
Okay.
And for Lie groupoids, there's not much difference.
Well, in fact, maybe not, because there are the counterexamples of Scandalis 2 and
for cross product for actions.
For actions.
On non-trivial coefficients, everything is false.
Yeah.
But that's for non-trivial coefficients. Kohn-Kasparov is for trivial coefficients.
Okay.
So, but I actually comment. So there is of course, version of periodic cyclic homology for C-star algebras, not for these smooth algebras that you wrote, that you have this C infinity CG, but for group C-star, for the groupoid C-star algebra. Okay, so and there is the local cyclic periodic homology for C-star algebras. I think the best versions are by the most readable versions by Ralph Meyer.
Okay.
Okay, and if BC holds for K theory, then it also holds for periodic cyclic homology. Okay, if you take this local periodic cyclic homology, it's kind of corollary. From where so the one for periodic cyclic homology is a corollary of the one for C-star algebras.
Okay.
I
don't know too much about this. I have seen some years ago the local version, but
yeah,
maybe you know more about this. But what about the formulas?
What about the
index formulas? You know,
formulas
for the pairings, because this is what was the main motivation. You know, these formulas of the pairings that you can get here require.
So formulas are the same. No, it's kind of formulas. If you know that the theorem holds, then the formulas are the same. It's kind of, in some sense, the formulas are kind of secondary because the formulas are kind of homotopy invariant. So if you know that the theorem holds, then your formulas hold.
Okay.
It's essential on this level. And so you always have this equivariant dot class, and you have your commuting diagram. This Grothendieck type commuting diagram, right? So that's the definition of dot genius. That's the difference between Thom isomorphism in K theory and Thom isomorphism in de Rham cohomology.
Yeah.
So difference between those two is essentially by definition is the dot genius.
Okay.
I think Paul can say a lot of things about it.
Yeah,
I think he
yes.
knows these things better than me.
You need to unmute Paul. Paul, you need to unmute.
I unmuted now.
Yes, yeah.
Yes.
Can you hear me now? Yes. With Kasparov, the situation there is very interesting. I mean, this is for connected, or maybe a finite number of connected components, Lie groups. As Richard said, this is not a conjecture, this is a theorem. But we now have a very interesting, even stronger result, which implies Kasparov, which is that if you take your original Lie group G, and then you form the, I don't know what to call it, the Mackey group, which is the cross product of the maximal compact subgroup acting on the quotient of the two Lie algebras. There's actually, Nigel Hickson worked on this for years, but the original idea goes back to Mackey. These two actually, there's a natural bijection between their irreducible representation. This is an even stronger result, which implies Kasparov. So we have that now. But I'd like this. What's up on my screen? We have the this orbifold.
Paul, it doesn't, because Paul, it's true for semi-simple Lie groups.
Semi-simple. Oh,
yeah, it does not cover the case of locally compact, almost connected
I
group.
see. So it's known for what, like SLNR, you know, for semi-simple, connected semi-simple.
Yeah, that's the Nigel's construction. Yeah, Kasparov holds for any locally compact, almost connected group. It also Kasparov also holds for p-adic groups.
Yeah, well, p-adic groups. I mean, this
as long as pi1 is finite, Kasparov holds for p-adic groups, which is quite different universe from Nigel's constructions.
But p-adic groups is a whole new and very interesting world that we should all, in my opinion anyway, that we should all pay attention to. So, but with the orbifold group, so you can develop this group with orbifolds instead of manifolds.
Yeah.
And then, of course, you get a map from the group using manifolds to the group using orbifolds. All of this is happening on the left side of the conjecture.
Yes.
So we have this vertical arrow from the group using manifolds to the group using orbifolds. I don't know, I cannot say for sure, but I suspect that this vertical map is always an isomorphism for any discrete.
Yeah, I think
it is an isomorphism, yes.
Oh, you know that for a fact?
It is an isomorphism, yes.
I see.
Well, I mean, I don't know a proof, but I have a proof. But yeah, I guess also, yeah, because essentially they both compare with the equivariant cohomology, for example, of the E-bar.
Yes.
And in fact, one can show that these two are isomorphisms, and this is commutative, of course. But of course, it's not trivial to show that this is an isomorphism.
Right.
But for example, in the paper we put it, we use very strongly your work with Hickson and Schick on the isomorphism on the geometric version of the left hand side with the analytic version to show that this is an isomorphism, and exactly somehow the same proof can be adapted to the orbifold case. Now,
good.
So in fact, this would imply, this would of course imply that this vertical thing is also an isomorphism. It would be very interesting to see how exactly it is, because given an orbifold, you have to somehow.
Oh, you in the meeting?
Yeah, I'm in the meeting.
Oh.
So sorry. So I was saying that to show that this is an isomorphism, when it somehow needs a geometric description of the inverse, And in fact, if you have an orbifold, of course, it's not a manifold, but somehow you need a desingularization of the orbifold to get a push for an
Yeah.
equivalent cycle.
Mhm.
So yeah, that's but of course it's a. I mean, again,
But you can do it actually.
It's an isomorphism. I mean, it's an isomorphism, of course, but and it would be very interesting to go further, because again, there are more singular manifolds than just orbifolds for which we know how to define higher indices, and it will be very nice, at least very interesting, I guess, to assemble these singular objects, because instead of using the classifying spaces, of course, they are not smooth, so one would like to approach them as smoothly as possible somehow.
Can I ask another question?
Yeah, please.
In the singular case, there is a version of the deformation to the normal bundle, which is called the deformation to the normal cone.
Yeah, in fact, this is what how I call it. Yeah.
Yeah. So, but in this singular case, I don't know if this cone can be given a structure of a groupoid, like it is possible for the normal bundle.
I don't know neither, but in fact, that depends. What we know is that if for a singular manifold, there is in fact what we call the non-commutative tangent space, which is in fact not a vector bundle, but it's a singular. It's a Lie groupoid. In fact, and is in fact constructed from these blow-ups, this deformation to the normal cones. But so the manifold itself maybe is singular, yes, but in fact its tangent space, there is a model at least, which is a Lie groupoid, and which is exactly constructed using deformation to the normal cones.
Are you using some desingularization to achieve this?
Yes, this is in fact by Deborg and Lescure. They define for X as stratified pseudo-manifold, pseudo-stratified manifold. They defined, so this is a very singular object. They define a non-commutative Lie groupoid, which is in fact from the K-theoretical point of view is the tangent, because it has the duality. So it's a decay homology of this space is in fact isomorphic to the K-theory of the tangent of the non-commutative tangent space. And this construction is exactly done using, in fact, the ideas of Hironaka. So it's a desingularization, but using blow-ups, so deformation to the normal cones.
Is the result on the level of your Schrick map independent of the choice of desingularization?
For the orbifolds, yes. But
but for orbifolds that are very mild singularities.
Yeah. No, the other, in fact, as far as I know, there's no Schrick construction, at least as I know it.
Not functorial, not functorial construction.
Yeah, well, not using this approach. Maybe there are other constructions.
Okay.
Yes. Not using this model. Yes.
Well, quote Grothendieck.
Yeah. Should
we are talking about discrete groups in this mainly, for the most part. This has been about discrete groups, right? In the talk.
Yeah.
And as Richard has said a number of times, what about with coefficients? I mean, the conjecture of Alain-Connes is most natural, I believe, with coefficients. Now, there are some remarkable, some people might say crazy, but some remarkable discrete groups which contain what's called an expander in the Cayley graph. And for these discrete groups, the conjecture of Alain-Connes as formulated, as we originally formulated, is not correct. It's not true, because these groups are not what are called exact. These groups are not exact. However, there's a paper which I recommend you. I recommend you this paper by me and Günther and Willett, in which we show that for non-exact groups, you have to change a little bit the formulation of the conjecture, and then the conjecture is true for these examples. So all the groups that you know and I know and we ever had anything to do with, all the locally compact and discrete groups, they are what are called exact. And there, I think the formulation of the conjecture should be the way that Alain Kahn and I originally did it. But when you get to these groups that have an expander and the Cayley graph, these are discrete groups, these are no longer exact, then you have to tweak a little bit the conjecture. And this is you have to make a change in the right-hand side of the conjecture. The left side of the conjecture seems to be correct. So the right-hand side of the conjecture has to be changed a little bit when you deal with groups that are not so-called exact. This is explained in the paper by me and Günther and Willett. I think there's only one paper by me and Günther and Willett.
So, I remember correctly that this is just changing the norm, taking something in between the reduced and maximal?
Yes, but what you do is, you take the minimal cross product. Yeah, it's a matter of what cross product you use for the right-hand side of the conjecture. You take the minimal, you change minimally from the reduced cross product. You make the smallest change you possibly can make, so that the group now looks, so to speak, as if it were an exact group. You take the minimal exact cross product. That's what you do. And this is explained in this paper by me and Günther and Willett. Where did that paper appear? I forget where it appeared, but it appeared. It's out there somewhere. I urge you to read that paper.
We'll do it tonight.
Yeah.
Oh, very good. Oh, I'm glad. Good. But all of this is with coefficients.
Okay.
That whole discussion is with coefficients. All right.
And Paul, do I remember correctly, it was Damian Osaida here in Wrocław who really proved that you have this expander in the Cayley graph?
Osaida in your hometown of Wrocław.
Yes.
Of course, the Americans say Wrocław.
Yes.
For some of us as well, but yes.
Your hometown of Wrocław, otherwise known as Wrocław, Osaida made an excellent contribution to all this. He showed in a very explicit way that these discrete groups can be constructed, that they exist. Previously, it was only a kind of a statistical probabilistic thing that due to Gromov, that these groups do in fact exist. But Osaida made an excellent contribution by showing by a very explicit construction that these groups exist with an expander and the Cayley graph.
Okay.
The point, Osaida's contribution was to make everything very, very explicit, very precise, rather than a kind of probabilistic statistical existence proof.
Okay,
so
great.
that was a very good thing that was done by Osaida in Wrocław.
Perfect. Yes. Anybody else? Any comments, questions? I don't see any raised hands. So are you sure, guys, that we release our speaker? Adam, you didn't ask a single question today.
So maybe let me ask a quite general question. So as I understood correctly, this isomorphism between this K dot topological and the K dot of this universal example is not so obvious, yes?
It was not so obvious. It was based in our approach, based on these previous computations that was mentioned in Baum-Connes and Schick, but also the decomposition, the delocalized decomposition, I would say, of Wolf and Luke and Mattei. So for discrete groups, it was based in a lot of work of many people. It was not so obvious.
So
Okay, so I have a remark about this. If
Yeah.
it's not so obvious, it requires a proof. You mean it's not obvious?
This is already proof. It's in the preprint. Well, I hope it's okay. But yeah.
Okay.
So not
I
obvious.
I have a
requires
comment about
proof, yes.
we have Gromov's principle, right? Which is that there is, according to Gromov's principle, there is no statement about all finitely presentable groups, which is both non-trivial and true.
Hmm.
Well, of course, here we have such statements. These are apparently non-trivial statements, which are true. But of course, you might say it's all on the left side of the conjecture. And then, anyway, I'm just saying maybe there's something here related to Gromov's principle. I mean, you could argue it's all on the left side of the conjecture, therefore it's trivial.
Or differently,
maybe
it's
let me ask
left side of a conjecture, because it's a kind of topological construction, period.
Right.
It's a construction.
Yes,
Okay? It's a construction.
yes.
The non-trivial statement would be that left and right side isomorphic. Right?
That's
But
the non-trivial. Yeah,
and
that's
that's the one where Gromov principle applies.
okay, yes. By the way, I asked Gromov, I said to Gromov, well, what if
Okay, and
yeah. I said, well, what if the conjecture of Alenkon is true? And I said, this would violate your principle. And I remember very clearly what Gromov said. He said, well, there can always be a first time.
Sorry, can I ask the same question, but let me be somehow more precise. So what is not obvious is that there is an isomorphism, but is it obvious that there is some natural map at least?
Oh yeah, because the cycle.
yeah, the map
In fact,
is yeah.
the map is obvious, yes, but essentially it comes from the duality, the Poincaré duality the Poincaré duality of for proper actions. I don't know how to say it, but essentially the Schrick map in K theory, that as I put it, is for proper actions. Is in fact there's a duality here for spin-C objects. Oh, sorry.
Screen disappeared.
Oh.
But at least the
Okay.
speaker did not disappear.
Well, maybe I won't. Yeah, maybe I don't have time to recover that again. But yeah, the map is obvious. So it's essentially, you know, if M has a proper action, then there is a map from M to the classifying space of proper actions. And in K homology, the map is natural.
Mm-hmm.
So then you need to pass from K theory to K homology, but there is a duality, which was proved by Kasparov and certainly by other people in this context.
Mm-hmm.
So the element of K theory, you transform it in an element of K homology, and then you push it.
Okay.
Yeah. Well, you have to show that this is well defined. So this is that the Schrick map coincides with the push forward in K homology.
Mm-hmm. Okay. Okay. Thank you.
Yeah.
All right. I don't see any other volunteers to ask questions. So let us thank our speaker again. Thank you, Paolo.
Thank you very much to everyone.
Thank you.
Thank you very much to
Nice
everyone.
talk.
Very nice talk. I stopped recording. Please don't go away.